On to chapter 9 today, but I wanted to give you a couple examples of SN2 and SN1 and E2 and E1 reactions in biology or in sort of modern chemistry. So I'm going to draw for you, and anytime I do this, show applications, the thing people want to ask, let me just tell you, do I expect you to memorize the structure of the molecule I'm drawing? No, I do not. I have not memorized it. That is why I'm looking at my notes. Okay, this is noradrenaline, and it is modified biologically in an SN2 substitution reaction to put a methyl group on the nitrogen, and then it becomes adrenaline. Now you can ask, how is it possible to modify the nitrogen without modifying the oxygen? That answer you should know. Which of those two is more nucleophilic, the nitrogen or the oxygen? The nitrogen, how do you know? For S, go ahead. Right, conjugate acid, so hydronium is a -2. Conjugate acid of an amine is like 9. So that's in our category of good nucleophiles. Another way of rationalizing it is nitrogen's just nitrogen's less electronegative than oxygen, so it's more willing to donate its electrons. Less electronegative means its lone pair electrons are higher in energy. Okay, so that's one issue. The second issue is, what is your reagent going to be in biology? For an SN2 reaction, you'd want something like this. Okay, well, we just got done talking about alkyl halides, so let's helpfully suggest to nature that it used this really electrophilic methyl iodide. Problem is, that is a DNA alkylator. So if biology used that, we would all look like this. Arg. So nature has developed a reagent that has a leaving group attached to a methyl. I'm going to call it nature's methyl iodide, but it's actually called, and you're going to hate this, please do not memorize it, S-adenosylmethionine. You'll encounter this again in biochemistry. Some people call it SAM. That's SAM-I-am, that's SAM-I-am. I do not like that SAM-I-am. Actually, you know, one of my research advisor, my PhD advisor's name is Sam Gelman. He's a great mentor and friend, but I kind of always have wanted to give him a copy of Green Eggs and Ham with his face pasted in the place of Sam-I-am. Never quite had the courage to do that, but maybe this is the year. S-adenosylmethionine is kind of weird, and I don't expect you to memorize its structure. It's kind of a modified amino acid / nucleotide. So I'm just drawing all of it, just basically so you can be scared of the complexity of biology. Make it stop. I don't think it was on the test. Was it? I don't think so. It could have been, maybe next year. So basically, you've got the methyl group here, and this really strange thing that you've never seen before. And I'm just going to say that this is a leaving group. Got it? And you can tell because if a nucleophile attacked, the electrons would go to the sulfur and it would be neutral instead of positively charged. Okay? Why does nature bother with all of this? Well, this particular amino acid is methionine, and so it uses this section of the molecule for other purposes. but it can turn it into a methyl transfer reagent by adding this group. Some of this is related to the enzyme holding on to the molecule, but in any case, this is the reagent for the conversion of noradrenaline into adrenaline, SN2. Okay, so that's going on inside you as we speak. The leaving group, once it leaves, I guess I'll just copy and paste because, oops, that's not what I wanted. Copy, paste, yikes. Let's erase. So this is the group that leaves, and this one is called S-adenosyl homocysteine, and it can be recycled into S-adenosyl methionine. Yeah, this does. Oh, yeah. We need to get rid of the positive charge on the sulfur. Here's the lone pair that left. Okay, so that's an example of an SN2 reaction going on inside you all the time. In fact, you'll later learn in 352 that this reaction is remarkable because a methylated amine, is more nucleophilic than this secondary amine is more nucleophilic than the primary amine starting material. So if you try to do this reaction in the lab, you're actually going to put more methyl groups on that nitrogen, because with each addition of methyl group, the molecule gets more nucleophilic and you can't control it. So it's beautiful that nature's able to do this. You want to do this reaction in the lab, we have to take a different strategy that you'll learn about in 352. All right, so that's a bio-SN2 reaction. Let's look at SN1. I told you that SN1 is not synthetically that useful in the lab. It is crazy useful in biology. So here is a reagent that's used biologically. Again, don't memorize the structure. This is called dimethyl allyl pyrophosphate, or DMAPP, and the two phosphate groups linked together. This functional group is called pyrophosphate. And as above, this is a good leaving group. And notice how it's on the allyl carbon. Right? You know what to do here. You know that if that leaving group left, you'd have a resonance stabilized carbocation. A lot of the time in molecules with multiple phosphates, you've got divalent cations like magnesium that are chelating some of those charges. But you can have the leaving group leave to give you a resonance stabilized carbocation. And then this can be a reactive intermediate for another reaction step. I'm going to show the resonance structure so that you can see that it's resonance stabilized. So one reactive step that can happen, you could have the pyrophosphate leaving group act as a nucleophile and come back in and attack this carbon. Sometimes that switch of the leaving group from this carbon to that carbon is important for biosynthesis. Another interesting step that previews a reaction we will see in chapter 10, I think, is the reaction of, and I tend to abbreviate this pyrophosphate group like that because I don't want to draw everything. This group can act as a nucleophile. The pi electrons are the HOMO of that molecule or the reactive portion of that molecule, and they can attack, whoa, that's not the right one. They can attack the positive charge. The enzyme would control which of the carbons gets attacked in that carbocation. That creates a new carbon-carbon bond, which I'll highlight in red. And
yeah. Is the one that's attacking, why is it on the terminal end?
This is a different molecule. This is called isopentenyl pyrophosphate. So they're actually isomers of each other, and the synthesis of either of them happens through the same pathway. It's just at the last step where the double bond is changes. Yeah?
Why would the pi bond be the HOMO and not the charge?
Yeah, thank you. I knew as I said that was going to be a problem. It's true, lone pair electrons on the pyrophosphate group could be reactive. Possibly it's just an issue of proximity. One of the ways that enzymes catalyze reactions is they bring two things together. And so in that case, the orientation provided by the enzyme can direct the chemistry to go in the desired direction. Yeah. All right, so let me ask you to predict. There were two atoms in this pi bond that are involved with these electrons. One of them is going to get the bond with this carbon, and the other is not. The other is going to get a positive charge. So if I number these carbons 1, 2, 3, 4, and 5, of 1 and 2, which one gets the new bond? And can you predict it? And then tell me why. Yeah?
One will get the new bond because the electrons in that double bond will move on 5, and just based off of proximity, I think it's more likely to have your methyl group sticking out rather than your like.
Okay. So you prefer attack of making a bond between orange 5 and purple 1. It sounds like for steric reasons.
Yeah.
Yeah. Okay. It's probably that's a good factor. What else? Yeah.
Well, I felt like it might be too, just purely out of stability, just because it's connected to more carbons, and so it can.
Okay. So you're thinking about alkene stability and the fact that this one is connected to more carbons. That is an important issue. Tell me what the intermediate's going to be after we make this after we make this new bond. Or rather, tell me something about is it one of these gets the bond, the other one gets what? Positive charge. Okay. So what do you know about carbocations? Right? You want the positive charge on the more substituted one because it's more stable. So you end up making the following molecule. Here is the new bond between orange 5 and purple 1, and we make that bond so that the positive charge can be on the more substituted carbon where it's more stable. Okay, so that's a new reaction you haven't seen before, but it makes sense in terms of principles that you know, and that's sort of a chapter 10 reaction. What we're going to do now is a chapter 7 and 8 reaction because we're going to do an elimination reaction, and it's this beta proton on purple carbon 4 that is the reactive one. There are other beta carbons available. This one would give you a less substituted alkene. This one would give you a similarly substituted alkene, but it doesn't, in terms of chemical strategy, you really want the double bond here so that this can be an allyl leaving group so you can do more chemistry. So nature's enzymes govern that process and make sure it's this enzyme, this beta proton that's reactive. And so your product is, let's see, yep. And this is called geranyl pyrophosphate, and it's an intermediate in the synthesis of a lot of natural products called terpenes. It's also an intermediate in cholesterol biosynthesis. And this is found all over in nature in sort of essential oils of plants. Don't get me started on essential oils. But actually, there's nothing wrong with essential oils, just none of the claims are verified by the FDA or by double-blinded, randomized controlled clinical trials. So anyway, I started. This molecule, the alcohol version, is called geraniol, and that's rose oil. Yeah? Do you get the terpene chemistry in OChem 1 or OChem 2? I forget. Usually I can't stop myself, and we do some of it in OChem 1. All right. So SN2 or SN1/E1 reaction from nature. Anything else you want to talk about there? You can see that we could add a ton more subunits to this to create longer molecules simply because we have an allyl leaving group. So you can actually go through this process again to add a third IPP molecule or a third equivalent of this unit. And anyway, a whole bunch of really cool stuff going on. Right. So now let's talk about Chapter 9, which is alcohols. Using alcohols as starting materials for substitution and elimination reactions. Okay, so now our starting material is an alcohol. And so to do a substitution reaction, I'm going to tell you this does not work very well. Let me show you what the desired products would be. This does not work well. This works great. Why? Okay, I'm hearing things about what? OH is a bad leaving group. Why is OH a bad leaving group? Okay, we talked about this maybe a little bit, but good leaving groups are conjugate acids. Oh, brother. Good leaving groups are conjugate bases of strong acids. That is, they don't mind being on their own. They can stabilize a lone pair of electrons. The conjugate acid of hydroxide is water, pKa 16. That is not a strong acid. So one of the things that's going to be a theme in this chapter, and the motivating purpose for most of what we do, is going to be that OH minus and OR minus are terrible, horrible, no good, very bad leaving groups. I'm not sure if any of you have ever read that book, but it's also kind of frustrating, isn't it? Right. So our strategy in this chapter is we're going to need a couple of different ways to turn the OH into a good leaving group. One of these is easy to do but has some undesired consequences. Can you think of what we might do to this alcohol to turn it into a good leaving group? Yeah? React it with an acid, good. If you do that, that's acid-base chemistry. Let's use HCl, for example. What does that do for us? That protonates the OH, thereby converting it into, how about now? What is the conjugate acid of this? H3O plus pKa minus 2. Now we're talking. Now this is a good leaving group, and you can actually do this reaction where you use acid to protonate the OH, turn it into a good leaving group, and then the halide, you remember we said, and I told you we weren't going to worry about it in chapters 7 and 8, but you can use the halides as nucleophiles. It has to do with their size and polarizability. So you can actually do an SN2 reaction here where you remove the OH group as water, and then you generate an alkyl halide. Now, I think some of you may be looking at this and getting frustrated. Didn't we just learn how to turn alkyl halides into alcohols? Why on earth would we want to go backwards? And the answer is not sure, but in the process of making any large molecule, you may want to interconvert functional groups at different stages. The organic chemist who does synthesis likes to have a lot of options in the toolbox. So if we have a way of converting an alkyl halide into an alcohol, it's also nice to be able to go backwards too, and to have both options. So this is one way that you can do that. The problem, so strategy one is turn OH into a good leaving group by using acid. You know, I suppose that sounds like a hidden message of some kind, so protonate the OH. All right. Have a nice trip. Okay. The problem with this approach is that for secondary and tertiary alkyl halides, or sorry, secondary and tertiary alcohols, if you try to do protonate the OH group, the substitution reaction works, but you actually get both enantiomers of the product. What does that tell you about the mechanism? Can it be SN2? No. In fact, what likely happens is you protonate the OH group, turn it into a good leaving group. It's good enough to leave on its own. So the evidence is that it does, and you get a planar carbocationic intermediate which your nucleophile can attack from either above or below to give you these products. I will say at this stage that you have been told, so this is sort of an SN1 mechanism, right? Now in chapter 7 and 8, I told you there wasn't really much selectivity between SN1 and E1. Unfortunately, life is filled with exceptions to general rules. And your text doesn't rationalize this, and I am not really sure why. In the acid-based conversion of an alkyl or an alcohol to an alkyl halide, you generally, at least as far as the text is concerned, don't need to worry about E1 products. I don't know why. I certainly wouldn't count it wrong if you predicted that there might be some E1 products here. Yeah?
So just in those first two examples, you have bromine went, it replaced it, is that correct? Or I thought it was going to be the OH2 groups.
Right. This is we do protonate the OH group first, then it leaves, we get the carbocation, and then bromine attacks. Yep. So for some reason, we don't really observe E1 products. As I said, I'm not going to count it wrong if you show E1 products here and your text doesn't really explain why you don't get them. I suppose if you want a hand-wavy explanation for why it's that way, you could say, well, Br minus is a terrible base, and okay, sounds good, yeah.
Particularly with Br minus, or in all of these acid conditions?
HCl, HBr, same sort of thing. You don't tend to see elimination products, but you do see evidence for a planar carbocationic intermediate. So I told you that chiral starting materials are expensive. So this is kind of a boneheaded reaction to do with molecules that have stereocenters, because you're going to lose chirality. Now we're also going to introduce something else, another wrinkle that was going on the whole time, but which I didn't tell you about in chapters 7 and 8 because I was trying to be merciful and because your text didn't talk about it.
Thank you.
Yeah, well, you're going to hate it, but it's kind of cool, all right? So let's just let me give you the data and see if we can walk through the explanation. I'm going to use, so problem number 1 is carbocationic intermediate leads to loss of stereochemistry, meaning, by that I mean loss of optical activity, or you get both, it leads to racemization at that particular stereocenter. All right, a second problem is related to having a carbocationic intermediate. Here is a chiral secondary alcohol, and if you use HBr, you get as products the expected, and I'm just going to use one line to indicate that I have both enantiomers. Are we okay doing it that way, communicating it? Yeah? Okay. Understand that I know that that's a stereocenter, but with the line that's not dashes or wedges, I communicate I have both configurations of, this is fully equivalent rather to drawing the two separate enantiomers. But strangely enough, I observe another product. And that other product looks like this. Wait a minute. Oh, sure. Dun, 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 dun. What? Confirm. Yeah, take a minute, look at it, take it all, breathe it in, see, swish it around in your mouth. See, confirm that there's the same number of atoms in the molecule. How did the carbon switch sides? I'll give you a hint. It was not resonance, because resonance doesn't involve moving of atoms, right? This is what we're going to call a rearranged product. What happened? All right, well, let's look at the carbocationic intermediate, which is going to look like this, positive charge. And actually, let's take a closer view. Let's try to draw this in a plane. And we'll draw this methyl group coming out at us, this proton going away from us. And then, but still, all of these atoms are in the plane. I'm going to draw the empty p orbital represented by that positive charge. Okay. And then on this adjacent atom, whoa, just lost it. On this adjacent atom, we're going to draw the 3 methyl groups. I'm going to draw one of them lined up with the empty p orbital.
Are all 3 in the plane, or are we just showing them that way because it doesn't matter?
Yeah, so it's, from this perspective, it's kind of difficult to portray. This is a tetrahedral carbon. This carbon-carbon bond is lined up with this p orbital, and these two are angled down below the plane, sort of. If we wanted to, we could do sort of to the front and sort of to the back. If you want, we can look down that bond, and what we would see is 3 methyl groups in the front, methyl group here, a hydrogen here, and in the back, here's your empty p orbital. So that methyl group's lined up with the empty p orbital. Now, when a filled orbital lines up with an empty orbital, you have the chance for hyperconjugation, right? Which we've said, and I'm going to draw actually the plus combination here, sigma, carbon-carbon sigma plus the empty p orbital. Let's line them up with, the same wave function sign. Okay. Hyperconjugation allows delocalization of these electrons a little bit into that empty p orbital. So now I want to do a thought experiment. I want you to imagine whether it's possible for this methyl group to sort of start, since these electrons are delocalizing a little bit over here anyway. Yeah?
How does hyperconjugation, this is just if you're, how does hyperconjugation affect rotation about bonds?
How does hyperconjugation affect rotation around bonds? It creates a barrier to doing so because you have to lose hyperconjugation when you stop aligning things. Yeah. Right, so imagine that as these electrons start delocalizing over this way, that sometimes the methyl group starts to lean over too, right? Can you imagine, and if we were to actually draw what this orbital looks like, I would draw maybe a pi sort of, kind of like orbital, or a pi lobe between the two, you get continuous sort of overlap. So now imagine sort of moving the methyl group over so that it's sitting in the middle. And these electrons from that bond are now just shared kind of here. Yeah? So let me show you sort of what that would look like orbital-wise. You would have basically have a methyl group here. In between the two carbons, and the electrons from that original carbon sigma bond are now going to be in an orbital that kind of looks like a pi bond. There's 2 electrons in this orbital. They're just there. We're having a hard time figuring out what on earth is going on because we've not seen very often a situation where 2 pairs of electrons are shared over 3 atoms, except in the case of the allyl carbocation resonance, right? So the methyl group moves over. This sigma plus p hyperconjugation situation turns into this sort of situation where the methyl group is shared evenly between those 2 carbons. If you want, we can put dotted lines here to indicate that you have 3 atoms and 2 electrons involved in this semi-bond. Yeah?
So are the hydrogens also being shared out across the atoms?
These hydrogens?
Yeah.
No, the electrons that are being shared are these ones from the bond between the carbons originally. The other carbon-hydrogen bonds are spectators that are along for the ride. Yeah?
Now, when we're thinking of this, does this reaction occur like will the rearranged molecule be just as equal as like the one that we were like originally taught to do? Like, do they kind of appear at the same rate?
Okay, yeah, it's a good question. Do I expect one or the other of these to be the major product? I'm not going to ask you that question. There is a way, I'll take you through how you can predict when this is going to be a possibility. When it's a possibility, I'll just ask you to draw both options. Yeah?
So, if you drew an energy diagram of a hybridized orbital, for example, you drew the electrons in the plot right there. Would this be a sp3 sp hybrid orbital?
Yeah, probably, what's the hybridization of these carbons? Well, they're probably not tetrahedral and they're probably not 100% flat. So somewhere between sp3 and sp2. Yeah, and nature doesn't care what we call them. Actually, if you do, you can calculate the energy of this intermediate and calculate what this orbital looks like, and it looks just like that. It's literally like the methyl group takes its electrons and starts leaning over towards the positively charged carbon. You guys have seen While You Were Sleeping, no? Okay, you need to. It's a sort of fun Christmas movie. There's a whole line in there about, you know, Luce, is this guy bothering you? Because it looks like he's leaning. Anyway, look it up. It's funnier when you see it. Had to be there. The other day, I found myself trying to explain a funny commercial to other people, and I realized that that was probably not a great way to have a conversation. Right. So, imagine this is a transition state with double daggers, and as the methyl group continues to lean over, then it gets bonded to the other carbon. And now we have sort of the opposite situation where we have on the other carbon a positive charge represented by this empty p orbital. And then we'll put that positive charge here. And then we'll show the carbon-carbon bond here. You see how we can smoothly transition from the one to the other simply by moving the methyl group over? Yeah?
So it's like the methyl group equally sort of connected to both carbons?
In the transition state, yes, the methyl group's sort of equally shared between both carbons. This is called carbocation rearrangement. Now, give some thought to this over the weekend. What kind of carbocation is this? What kind of carbocation is this? And can you see why this thing might happen? What's the driving force for it? All right, I will stay tuned for an email, and I will see you Monday.